Кажется, никого нет, потому что сессия. Ой, да, но это вроде как прямого отношения не имеет к самой лекции. Ну ладно. Нет, ну ладно, может посмотрит запись. Впрочем, бывало так, что я читал, когда вообще никого не было. Только просто на камеру. Okay, so at the previous lecture we began to discuss the Hanbano Theorem. Let's recall the statement of this result. Suppose that we have a semi-normed space. X is a semi-normed space. As usual, over the field of real numbers or over the complex numbers. So bold K denotes our base field. Also, suppose that we have a vector subspace x0, vector subspace of x, and a linear functional defined on x0. Let's also suppose that f0 satisfies the following estimate. It is dominated by the semi-norm in the following sense. Everywhere on x0. The theorem states that there exists an extension, there exists a linear functional f, defined everywhere on x, which extends f0, and satisfies the same estimate everywhere on x. Well, I'd like to stress once again that the essence of this theorem is here in this estimate. So without this estimate, the theorem would be a trivial result from linear algebra. So the point is that we can find an extension of f0 which satisfies the same estimate everywhere on the space x. The proof, the strategy of the proof is as follows. First, we will prove the result over the real numbers, and then reduce the complex case to the real case. The proof of the real case consists of two steps. And the first step was already done at the previous lecture. This is case 1. A special case. This is the case where x0, the subspace x0, has codimension 1. That is, there exists a non-zero vector, little y, in x such that we have the following direct sum decomposition. So in this case, the result was already proved at the previous lecture. So I'll not repeat the proof once again. Well, let's now look at the general case. The general case is a standard application of Zorn's lemma. So we consider the set of all possible extensions of f0 to intermediate subspaces. So formally, we consider the set M whose elements are pairs Z and G, where Z is a vector subspace containing x0, And G is the linear functional on Z. Which extends F0 and satisfies this estimate everywhere on Z. So this is our set M. This is the formal definition, and the meaning is that it consists of all, in a sense, admissible extensions of F0. Admissible means that they satisfy the same estimate. So let's now make this set into an ordered set. So we introduce an order relation on M as follows. You have two such pairs, Z1, G1, and Z2, G2. We say that the first pair is less than or equal to the second one if Z1 is contained in Z2 and G2 extends G1. A very natural order relation. So clearly M becomes a partially ordered set, and it's a simple exercise to show that M satisfies the conditions of Zorn's lemma. This is quite natural. So if we want to show that this is indeed the case, we must show that every chain, every totally ordered subset has an upper bound. Well, if we have a chain of such subspaces and linear functionals which extend each other, we can just take the union of this chain. And this will be the upper bound for our chain. So the conditions of Zorn's lemma are satisfied, and hence M has maximal element. There exists a maximal element, that's denoted by Z and F, maximal element of M. I claim that Z actually is all of X. Well, why is it so? If this is not the case, then take any element y in X which doesn't belong to Z. And let Z1 denote the direct sum of y and of the one-dimensional space spanned by y and Z. so that Z is of codimension 1 in Z1. And apply case 1. Case 1 implies that there exists a linear functional G1 on Z1 which extends F and which satisfies the same estimate. In particular, we see that the pair Z1, G1 also belongs to the same set M. And is strictly bigger than ZF. So have a strict inequality here. But this is obviously a contradiction with the maximality of ZF. So the contradiction implies that z equals x. And this completes the proof of the real case, because now f is defined everywhere on x. And since this is an element of M, we see that f satisfies the required estimate. So this completes the proof in the real case. Now what we want to do is to reduce the complex case to the real case. We'll need the following simple lemma, which is actually a purely algebraic lemma. Suppose that X is a vector space over the complex numbers. And let XR denote the same space considered over the real numbers. X considered as a vector space over the real numbers. Clearly this is possible because real numbers is a subfield in the complex numbers. Sometimes this space is called the realification of X. So we simply forget about the complex structure on X and consider it over the real numbers. And let's consider the following map, which is denoted by alpha. This map acts from the space of all complex linear functionals on X. So this is a little bit extended notation for the space of all complex linear functionals on X. And this alpha acts to the space of all real linear functionals on the realification of X. And alpha acts by the following simple formula. It takes f to the real part of f. So clearly the real part of a complex linear functional is a real linear functional. I claim that this map is a bijection. This map is a bijection. And moreover, we have an explicit formula for the inverse map. Alpha inverse takes each real linear functional G to the complex linear functional given by the following formula. The proof is a simple exercise for you. This is just straightforward calculation. So what we want to show, formally we have to show that first of all, this formula indeed defines a complex linear functional. So this is an element from this set. Clearly the real part is G. And finally we have to show if G comes from F, if G is the real part of some complex linear functional f, then this formula just is just f. This is just the same original functional f. But this is absolutely straightforward, just a few lines. Okay, so now let's apply this lemma to the complex case of the Hanbano theorem. The proof of the Hanbano theorem over the complex numbers. So we have a complex linear functional f0 on x0, and let's take its real part. Let g0 be the real part of f0. Well, this is a real linear functional on x0. And clearly, it's also dominated by our seminorm. This is true for f0, so this is obviously true for the real part of f0. So by the proof of the real Hanbano theorem, we can extend g0 to x. we already know that there exists a real linear functional g on x which extends g0 and satisfies the same inequality. So g is a real linear functional. Now we apply this construction that f be the alpha inverse of g. So by lemma f is complex linear. And it clearly extends f0 because the restriction of f to x0, by construction, this is alpha inverse of g restricted to x0, that is alpha inverse of g0. And since g0 is the real part of f0, we conclude from the lemma that this is f0. This follows from the lemma. So to complete the proof, we have to show that f is also dominated by the same seminorm. Well, let's take an element x in our space, and let's write f of x. So f of x is a complex number. We can write it in the polar form. So this is the absolute value of f of x multiplied by a complex number of the following form. Of course, each complex number can be written in this form. Okay, now this implies that the absolute value of f of x is f applied to the exponent of minus I phi multiplied by x, because f is complex linear. So we have this formula. But now, well, this is the absolute value of a complex number. In particular, this is real. Since this is real, we can replace f by g here. The imaginary part is 0, so f and g take the same value on this vector, simply because it is a real. Okay, now g is dominated by, but we know that g is dominated by the norm, the seminorm of x. So this is less than or equal to the seminorm of this vector. And since the absolute value of this number is 1, this is just the seminorm of x. And that's it. So we see that f is also dominated by our seminorm. And this completes the proof. Okay, well, I have already said at the previous lecture that the Hanbano theorem is one of the most fundamental results of the classical functional analysis, in the sense that it is in the fundament, so it is at the foundation of functional analysis. Almost all results, in almost all interesting results in functional analysis are actually based on the Hanbano theorem, either explicitly or implicitly, but this is a very essential result. So let's try now to deduce some interesting corollaries of the Hanbano theorem. Corollary 1 is almost equivalent to the original statement, but it is a little bit more convenient to us. So suppose that X is a norm space. X is a norm space. X0 is a vector subspace of X. Then, for each bounded linear functional f0 on x0, there exists a bounded linear functional f on x which extends f0 and has the same norm. So we have a norm-preserving extension, an extension of the same norm. Well, to prove this corollary, we just apply the Hanbano theorem. To x equipped with a new norm, now it's denoted by prime, where the new norm is just the old norm multiplied by the norm of f0. And this gives us our functional f. Well, clearly, by the definition of the norm of f0, f0, the absolute value of f0 of x is less than or equal to this new norm of x. So we extend f0 by using the Hanbano theorem, and we get an extension whose norm is less than or equal to the norm of f0. But of course, it cannot be strictly smaller because f extends f0. So the norms are the same. Okay, corollary 2. Corollary 2. If x is a norm space, then for each non-zero element, little x in our space, we can always find a linear functional f on x such that the norm of f is 1 and such that f of x is the norm of x. In particular, we see that f of x is non-zero because x is a non-zero vector. To prove this corollary, we first define f on the one-dimensional space spanned by x. We let f0, well, clearly there is a unique, a unique linear functional f0 defined on the one-dimensional space spanned by x. Such that f0 takes x to the norm of x. Well, and if we now take an arbitrary element in this one-dimensional space, we clearly have the following equality. The absolute value of f of y is just the norm of y for each element y in this one-dimensional space. Simply because y is x multiplied by a number. So we can now apply, so this equality in particular implies that f0 is bounded and the norm of f0 is 1. The norm of f0 is 1. So we can now apply corollary 1. Corollary 1, yeah. So corollary 1 implies that we have a linear functional f which extends f0 and has the same norm, that is, the norm of f is 1. Corollary 1 yields f. Corollary 2 implies, in particular, that bounded linear functionals separate the points of x. This is corollary 3. If x is a normed space, then for each pair of elements, x1 and x2, of different elements, we can find a linear functional, a bounded linear functional f, such that f of x1 is not equal to f of x2. That is, bounded linear functionals on a normed space separate the points. So morally, this result means that the dual space is big enough. It separates the points of x. To prove this corollary, we simply apply corollary 2 to x1 minus x2. So this is a non-zero element. We find linear functional f such that f applied to x1 minus x2 is non-zero, but equivalently this means that these two numbers are different. Corollary 4 is essentially an equivalent but useful way of writing corollary 2. Again, if x is a normed space, then for each element x in our space, we have the following useful formula for the norm of x. Namely, the norm of x is the supremum over the closed unit ball of the dual space, the supremum of f of x, where f runs over the unit ball of the dual space. And actually, this supremum is attained, so I can write the maximum instead of the supremum. Well, there is no need to prove this. This is equivalent to corollary 2. Indeed, if x is 0, then there is nothing to prove. If x is 0, then all three numbers are 0. And if x is non-zero, we apply corollary 2. So clearly this supremum, by the definition of the norm of f, this supremum is less than or equal to the norm of f. But on the other hand, corollary 2 implies that we can always find a linear functional f which is in the unit ball, for which this supremum is attained, and such that the norm of x is the absolute value of f of x. So this follows from corollary 2. So the meaning of this formula, that it gives us the explicit expression for the norm given in dual terms, that is, in terms of the dual space. In other words, more this means that we can reconstruct the norm of x from the dual space. Okay, corollary 5 looks a little bit more general than corollary 2, but we will see that it is equivalent to corollary 2. So suppose that x is a normed space. X is a normed space. X0 is a closed vector subspace of x. Then I claim that for each element in x which does not belong to x0, we can find a linear functional f on x such that the norm of f is 1, such that f vanishes at x0, and such that f of x equals the distance between x and little x and x0. So note that this is a positive number. This is strictly positive because x doesn't belong to x0 and x0 is closed. So in some sense, this corollary means that we can use linear functionals to separate points from closed vector subspaces. So little x doesn't belong to x0, so we can separate little x from x0 by using this functional. It vanishes at x0, but it doesn't vanish at little x. So formally, this is a more general result than corollary 2. If x0 is the 0 subspace, then what we get is exactly corollary 2. But actually, it turns out that this result easily reduces to corollary 2. Namely, we apply corollary 2 to the quotient. Apply corollary 2 to the respective element in the quotient of x modulo x0. So x0 is a closed vector subspace. We can take the quotient. It's a norm space. And this element is not 0 in the quotient because x is not in x0. So we apply corollary 2, and we get a bounded linear functional g on the quotient such that the norm of g is 1, and such that g applied to this vector is exactly the norm of this vector. Well, but let's now recall the geometric interpretation of the quotient norm. The quotient norm is just the distance between x and little x and x0. And now to construct the functional f, we simply compose g with the quotient map. F is g composed with q, where q is the quotient map of x onto x0. So we easily see that f is exactly what we need. It is a bounded linear functional. It vanishes on x0 because q vanishes on x0. So f of x is the distance between x and x0. And finally, the norm of f is 1 because q is a coisometry. Q takes the open unit ball of x onto the open unit ball of the quotient. So this implies that the norm of f equals the norm of g. Okay. Let's now introduce an important notion of a dual operator. So an important property of the construction of taking the dual is that this construction is defined not only on objects but also on morphisms. That is, not only on norm spaces but also on bounded linear operators between norm spaces. So suppose we have two norm spaces, x and y. Normed spaces. And T is a bounded linear operator from x to y. We define the dual of f, the dual of T, the dual of T is a map T star from y star to x star given by the following formula. Actually, there is only reasonable way to write such a formula. If f is a linear functional on y, we simply compose it with t, and what we get is a bounded linear functional on x. It is bounded because it is the composition of two bounded operators. So clearly, T star is a linear map. Clearly, T star is linear. Some Russian terminology. По-русски иногда говорят двойственное пространство и двойственный оператор. Иногда говорят сопряженное пространство, сопряженный оператор. Это синонимы. По-английски, кстати, тоже. So another synonym is the adjoint operator. And sometimes X star is called the adjoint space of X. But maybe the word dual is a bit better because a bit later we discuss adjoint operators between Hilbert spaces. Adjoint operators are closely related to dual operators, but formally they are different. So that's why I prefer to use the word dual instead of adjoint. So clearly T star is linear, but actually it is bounded. We have the following simple proposition. T star is bounded, and the norm of T star equals the norm of T. The proof is a nice application of the Hanbano Theorem. Without this theorem, we could only prove that the norm of T star is less than or equal to the norm of T. But the Hanbano Theorem implies that we have an exact equality here. Well, indeed, what is the norm of T star? So we will write a chain of equalities which implies both that T star is bounded and the norm of T is equal to the norm of T star. Well, by the very definition of the norm, of the operator norm, this is the supremum over the unit ball of y star. So what is this? This is a bounded linear functional on x. Again, we use the definition of the norm of this functional. So we keep the supremum and write explicitly the norm of this functional. Again, this is the supremum over the unit ball of x. So we must apply this functional to little x and take the absolute value. Okay, now we do the following. We can easily interchange these to suprema. The result will obviously be the same. And finally, by the definition of the dual operator, this expression is f applied to T of x. And now we apply corollary 4 to the vector T of x. We apply corollary 4 to this vector, and we conclude that this suprema over f is nothing but the norm of T of x. So we get this number. But what is this? By the very definition of the norm of T, this is just the norm of T. And that's it. So this chain of equalities implies that T star is bounded, and the norm of T star equals the norm of T. Let's now look at some simple properties of dual operators. One more proposition. First of all, the operation of taking the dual is linear. we have the following equality. So this equality holds for each pair of bounded linear operators from x to y, and for each pair of numbers lambda and mu. Second, if I have two composable operators, s and t, for example, tx from x to y and sx from y to z, then the dual of their composition is the composition of their duals, t star s star. Here s is a bounded operator from, t is a bounded operator from x to y, and s is a bounded operator from y to z. And one more remark, which is absolutely trivial, but which is useful. The dual of the identity map of x is the identity map of the dual space. The proofs of all three identities are absolutely trivial, so I leave this as an exercise for you. In particular, properties 2 and 3, so a little comment for those of you who are familiar with the language of categories. Properties 2 and 3 mean that the operation of taking the dual is actually a functor, a contravariant functor from the category of norm spaces to the category of Banach spaces. Here is a useful corollary of this proposition. If T is a bounded linear operator from x to y, I claim that, first of all, if T is a topological isomorphism, then so is the dual operator. And similarly, if T is an isometric isomorphism, T is a topological isomorphism, and so is T star. And if T is an isometric isomorphism, then so is T star. Well, from the general viewpoint, this is absolutely trivial, because each functor takes isomorphisms to isomorphisms. For completeness, let me prove the second part. Roughly the proof, not roughly, but essentially the proof means that we can consider the category of norm spaces and contractive linear maps. Some time ago I denoted this category by norm 1. So the morphism, the objects are norm spaces, and the morphisms are linear contractions, that is, bounded linear operators of norm less than or equal to 1. So this proposition, together with this equality, means that we can consider the operation of taking the star, of taking the dual, as a functor on this category. So explicitly, the proof of 2 looks as follows. We observe that T is isometric isomorphism. T is an isometric isomorphism if and only if it satisfies the following condition. There exists a bounded linear operator S which acts in the opposite direction from y to x, such that it is the inverse of T. That is, the following formula hold. and such that the norm of S, the norm of T is less than or equal to 1, and the norm of S is less than or equal to 1. So this is going to say that T is an isometric isomorphism. Well, indeed, these two conditions mean exactly that S is a homeomorphism, is a topological isomorphism. So this just means that S is the inverse of T. And a bijective linear operator, a little observation is that a bijective linear operator is an isometric isomorphism, if and only if it is contractive, and the inverse map is also contractive. Okay, now if this is indeed the case, then we can now just apply the star, and we conclude that T star S star is 1. S star T star is also 1. The identity map of Y star. The norm of T star is less than or equal to 1, and the norm of S star is also less than or equal to 1. So we simply apply these stars everywhere, and we get this. We get these conditions. But this implies that T star is an isometric isomorphism. The proof of part 1 is similar, and in fact is even easier than the proof of part 2, because we don't have to control the norms. By the way, an announcement. A bit later we will be able to prove that if X and Y are Banach spaces, then both implications are actually equivalences. This is much more interesting because this is, well, this proposition is just an implication of the category theoretic fact, a very trivial fact that a functor takes isomorphisms to isomorphisms. But the reverse implication is not so trivial, and it follows from some analysis. Okay, our next goal is to describe explicitly the duals of some operators, of some classical operators. Before we can do it, let's introduce a suitable notion of isomorphism between bounded linear operators. In fact, we will have two different versions of isomorphism, just like in the case of spaces. You have two normal spaces, we have the notion of a topological isomorphism and the notion of an isometric isomorphism. Which is much more strict. And similarly, we have two different notions of isomorphism between linear operators. So we give the following definition. Suppose that X and Y are normed spaces. Suppose that S is a bounded linear operator on X. So let's recall that B of X is a short notation for the space of operators from X to itself. And T is a bounded operator on Y. And suppose that we have a bounded linear operator U from X to Y. Then we say that U is a similarity respectively an isometric equivalence between S and T if the following two conditions are satisfied. First of all, we require that U should be a topological isomorphism, respectively an isometric isomorphism. And second, the following diagram commutes. This is S from X to X. This is T, which acts from Y to Y. And here we have U. So condition 2 is that this diagram commutes. And in this case, if there exists such an operator U, we say that X and Y are similar, or respectively are, not X and Y, S and T. S and T are similar, respectively, isometrically equivalent. S and T are similar. Respectively, isometrically equivalent. If there exists such an operator U. In Russian, similar is подобный. Операторы подобны. Ну, а U это подобие. So we have two natural notions of isomorphism between linear operators. And by using this notion, we can now describe the duals of some classical operators. I have the following proposition. Suppose that P and Q are real numbers between 1 and infinity, satisfying this relation. So we know that in this case, we have a canonical isomorphism between LQ and the dual of LP, and the other way around. Now let's consider some classical operators on the little LP space. First of all, we can take a diagonal operator. So suppose that lambda is a bounded sequence, and let m lambda denote the diagonal operator on LP. Let's add the superscript p here in order to somehow remember the space on which the operator acts. So lambda p will be the respective diagonal operator on LP. Let's also consider the right shift operator, TRP, on LP. Right shift operator. And the left shift operator, TLP. The left shift on LP. Okay, and let's now recall that we have a standard isomorphism between LQ and the dual of LP. That's denoted by alpha. L from LQ to the dual of LP. Standard isomorphism, which was constructed at the previous lecture. I claim that this isomorphism alpha is an isometric equivalence between the following operators. First of all, it is an isometric equivalence between the diagonal operator on LQ, m lambda q, and the dual of the diagonal operator on LP, m lambda p star. Second, I claim that alpha is an isometric equivalence between the right shift operator on LQ and the dual of the left shift operator on LP. And the other way around, it is an equivalence between the left shift on LQ and the dual of the right shift on LP. The proof is absolutely straightforward. So this is an exercise for you. We already know that alpha is an isometric isomorphism. So to pull this result, we just have to check the commutativity of the respective diagrams, which is absolutely straightforward. Another nice application of the Hanbano theorem is that each normed space can be canonically embedded into the bidual, into the second dual space. So we are going to discuss the canonical embedding. Canonical embedding into the bidual. And reflexive spaces. Well, first of all, what is a bidual? The bidual is the dual of the dual. So suppose that X is a normed space. Then the bidual of X is the space X double star defined in the following way. It is the dual of the dual. In Russian we usually say второе двойственное или второе сопряженное. Ну, говорят, что иногда дважды двойственное. То же самое. Okay, so this is, of course, this is a Banach space because the dual of any normed space is complete. Let's now introduce some notation. If little x is an element in our space, we define the evaluation map, evaluation functional epsilon x from x star to the base field by the following simple formula. This is just the evaluation at x. Well, clearly this is a linear functional. Epsilon x is linear. Well, we have the following simple proposition, which is also a corollary of the Hanbano theorem. Epsilon x is bounded. This is not a corollary of the Hanbano theorem. This is more or less easy. But what follows from the Hanbano theorem is that the norm of this functional is exactly the norm of x. This is exactly the norm of x. Without the Hanbano theorem, we could only prove that this norm is less than or equal to the norm of x. But actually, it is equal to the norm of x. Well, indeed, what is the norm of epsilon? By definition, this is the supremum over the unit ball, epsilon x of f, where the supremum is taken over the unit ball of the dual. but epsilon x of f is just f of x. And corollary 2 from the Hanbano theorem means that this number is precisely the norm of x. This follows from corollary 2 of the Hanbano theorem. So epsilon x becomes an element of the bidual of x double star. And we can now define the so-called canonical embedding. The canonical embedding of x into x double star is the following map. Let's denote it by Ix from x to x double star. So this map takes each element little x to the evaluation functional epsilon x. Well, the previous proposition implies that this map is actually an isometry. So this proposition implies that Ix is an isometric embedding. By the way, this construction gives us a very simple proof that each norm in space has a completion. This is a short remark, which is maybe not so important because we already know that each norm in space has a completion. But if you remember, the proof was a bit elementary but a bit tedious, so we had to check that some limit exists. Doesn't depend on the choice of the approximating sequence and so on. So now we can give a very simple proof. A simple proof of the fact that each norm in space x has a completion. Well, indeed, we take a norm in space x and we define the completion of x to be the closure of the image of x under the canonical embedding. So what can we say about the space x tilde? Well, it's a closed subspace in x double star, but x double star is a Banach space. So a closed subspace of a Banach space is also a Banach space. So x tilde is a Banach space. And the canonical embedding gives us an isometric embedding of x into x tilde with dense image. So x tilde is indeed a completion of x. Okay. An important property of this construction, I mean the construction of the canonical embedding, is that the canonical embedding of all norm spaces are compatible to each other in the following sense. I have the following proposition. For each bounded linear operator, T, from x to y, where x and y are norm spaces, the following diagram commutes. The following diagram commutes. So what is the diagram? We have our operator T from x to y. We also have the canonical embedding of x into the bidual, x double star, and the canonical embedding of y into the bidual, y double star. This is Ix, and this is Iy. And we also have the bidual operator from x double star to y double star. So tx from x to y, the dual operator x from y star to x star, and so the bidual operator again x from x double star to y double star. And I claim that this diagram commutes. So in some sense, the bidual operator becomes an extension of T. If we identify x and y with the subspaces of x double star and y double star canonically, and then T becomes the restriction of T double star. The proof is an explicit calculation. So this is an exercise for you. This is absolutely immediate from the definition of the bidual operator and from the definition of the canonical embedding. And from the viewpoint of category theory, this result means that the family of all canonical embeddings is a natural transformation from the identity functor on the category of normal spaces to the functor of taking the bidual. Let's now introduce an important notion of a reflexive space. We say that a normed space X is reflexive if the canonical embedding into the bidual is an isomorphism. Is an isometric isomorphism. Well, in fact, we already know that it is an isometry, so it is an isometric isomorphism if and only if it is surjective. What can we say about reflexive spaces? Well, first of all, we have an obvious necessary condition. Let's observe that if X is reflexive, then it is complete. That is, it's a Banach space. Well, indeed, X double star is always a Banach space. So if we have an isometric isomorphism between X and X double star, then X has to be a Banach space. How about examples? Perhaps the simplest example is a finite dimensional space. Example 1. Suppose that X is finite dimensional. Well, we know that in this case, the dual space is also finite dimensional, and moreover, the dimension of X star is the same. Well, indeed, we know from linear algebra that the algebraic dual has the same dimension. But since X is finite dimensional, we had an exercise in exercise sheet 2 that all linear functionals, all linear operators from a finite dimensional normed space are bounded automatically. So all linear functionals are bounded. X star equals the algebraic dual in this case, and it has the same dimension as X. Now we iterate this argument, and we conclude that the bidual also has the same dimension as X. And of course, an injective map from a vector space to the vector space of the same dimension is automatically an isomorphism. Again, a simple fact from linear algebra. X is an isomorphism, and so X is reflexive. Okay, let's now look at something infinite dimensional. Example 2. We take any real number p between 1 and infinity and find the respective q. Of course, there is a unique q satisfying this condition. So I claim that LP is reflexive. To show that LP is reflexive, let's look at the following picture. So first of all, we have the canonical embedding of LP into the bidual. LP double star. This is the canonical embedding. Next we have a standard isomorphism between LP and the dual of LQ. It acts from LP to the dual of LQ. That's denoted by alpha PQ, standard isomorphism. It is an isomorphism. But clearly P and Q are interchangeable, so we also have a standard isomorphism from LQ to the dual of LP. This is alpha QP. And the dual of alpha QP, alpha QP star, acts from here to here. It is also an isometric isomorphism between these spaces. We already know that the dual of an isomorphism is an isomorphism. And a straightforward calculation shows that the diagram commutes. This is a simple exercise. So this obviously implies that this arrow, the horizontal arrow, is bijective, so LP is reflexive. And the similar argument shows that the big LP spaces are also reflexive. A similar argument shows that LP of X mu is reflexive. Here P is again strictly between 1 and infinity, and X mu is an arbitrary measure of space. A short warning about this proof. There is a very popular proof, which is much shorter than mine, but which is wrong. A short proof that LP is reflexive. Well, we know that the dual of LP is isomorphic to LQ. And for the same reason, the dual of LQ is isomorphic to LP. By combining these two facts, we conclude that LP is reflexive. But this is not correct. If we formally combine these facts, we can see that LP is isomorphic to the bidual. But in fact, this doesn't imply that LP is reflexive, because there exist Banach spaces X such that X is isometrically isomorphic to the bidual, but X is not reflexive. The point is that a reflexive space should be canonically isomorphic to the bidual. That is, a very concrete map, the canonical embedding, must be an isometric isomorphism. But theoretically, it can happen that there is another map which is an isomorphism, but the canonical embedding is not an isomorphism. And such spaces do exist. They are quite exotic. Well, not very exotic, but are rather exotic. So unfortunately, I cannot construct them in this introductory course. Perhaps the most famous example of such a space is the so-called James space. It is a certain Banach space of sequences, and one can show that it is not reflexive, but is isometrically isomorphic to the bidual. So the point is that these two facts don't imply that LP is reflexive. So this proof is not correct. Okay, how about other classical Banach spaces? Well, this is an exercise for you. First of all, try to prove that all Hilbert spaces are reflexive. All Hilbert spaces are reflexive. For separable Hilbert spaces, this follows from the fact that it is isomorphic to the little L2 space. But I recommend you to give a straightforward proof which doesn't use an isomorphism between our space and little L2 space. So Hilbert spaces are reflexive, and the second, C0, little L1, or little L infinity, the space of continuous functions on the interval, and in fact many other classical Banach spaces are not reflexive. Okay, so that's all for today. Next week we will have a midterm exam, so I'll send you the details by email. And after the exam, so in 2 weeks we'll continue our discussion of dual spaces, and we find some relations between properties of operators and properties of the dual operators, which are quite useful. And then our next goal will be to prove two rather important theorems, which are also in the foundation of classical functional analysis, namely the open mapping theorem and the Banach-Steinhaus theorem. And that's all for today. Thank you.